Hi there, Mr. Sutton here with the AB Calculus 6-9 homework answers on accumulation. On this problem, we have the number of bacteria in a culture growing at this rate right here, and at time 0 there's 7,500 of the little guys there. So we want to find the number present at time 5. So we have the present amount, we have a rate of change, we want a future amount. This is basically a fundamental theorem of calculus in bacteria form. So we're starting with 7,500. We're going to add to that the integral from 0 to 5 of this rate of change that they just gave us. And for this, since we're doing this without a calculator, we're going to have to take the antiderivative. So let's see, this is going to be 3,000 e to the 2t over 5 times the reciprocal of this inner tail here. So we're multiplying by 5 over 2, which that's really 2.5, so this is really going to be 7,500 that's turning into. And we're evaluating that from 0 to 5. So I'm going to pull the 7,500 out of this bracket here, and inside I'm going to have e to the 2 times 5 over 5 minus e to the 0 times 2 over 5. Now let's go ahead and just simplify this because all the answers are simplified. So this inside here, this is really e squared. So we have 7,500 e squared, and then this is really just e to the 0, so minus 1. So when the dust settles, we have 7,500 plus 7,500 e squared minus 7,500. These first and last terms cancel, leaving us with just 7,500 e squared, which gives us choice C. On this problem, we're told that at time 0, a forest has 1,500 deer in it, and the rate of growth of that population of deer is modeled by this R of t function. It's an exponential function in deer per year. We want to know the population at time 3. Since I have one population value and I have the rate of change of population, I can figure out other values by using my fundamental theorem. So I'm going to let P represent the population, and I'm going to say that P of 3 is going to be equal to P of 0, which is 1,500, plus the integral from 0 to 3 of that rate of change of R of t dt. This is the deer at year 0 plus the change in deer, the total change in deer from years 0 to 3. So let me go to my calculator for this. So on Desmos, let me start by entering R of t in there, and that is 2,000 e exponent 0.23t. And then I'll do a new entry, and we'll just do 1,500 plus the integral int from 0 to 3 of R of t dt. And that comes out to approximately 10,141, and that's going to be deer. So that's going to be choice D, D for deer. For this problem, we have water being pumped into a tank at a rate given by this R of t function, and that's in gallons per minute, and t is the number of minutes since our pump was turned on. If the tank contained 800 gallons of water when the pump was turned on, how much water to the nearest gallon is in the tank after 20 minutes? So we're starting with 80 gallons, that's times 0, and we have the rate of change of gallons given here, and it's a positive rate, gallons are being pumped in. We want to know a new value of gallons after 20 minutes. So we're going to use our fundamental theorem on this. We can say that the amount of water in the tank, which I'll call just big R of t, R of 20, that's going to be the initial 800 gallons we started with, plus the change in gallons over 20 minutes. To get that change, I need to do the integral from 0 to 20 of R of t dt. And this is a calculator problem, so let me go ahead and see what that gives me on the calculator. So let me start by putting R of t in there as its own function. That's 30, and we have 1 minus e exponent negative 0.16t, and then we can close all of that. And now I want to do 800 plus integral int of 0 to 20, and then R of t dt. And that comes out to about 1,220 gallons if we round it off to the nearest gallon. So that's going to give us answer choice D. For this calculator-based free response problem, we have traffic flow defined as the rate at which cars are passing through an intersection in cars per minute, and the flow at a particular intersection is modeled by this big F of t function. So it's basically just a sine function, and that's only defined between times 0 and 30. All right, so to the nearest whole number, part A here, nearest whole number, how many cars are passing through our intersection over the 30-minute period? So we have the rate at which the number of cars is changing here, this f of t, the rate at which cars are passing through. If we want the total cars, we just have to take the integral of this over the period from 0 to 30. So we'll just do integral 0 to 30 of big F of t dt, and that's all I have to show before plugging this in my calculator. So let me go to the calculator. So I'm going to start by entering this big F of t function in here. So we got F of t equals 82 plus 4 sine, and then parentheses, t divided by 2, and close that. And let's go ahead now and do this. So integral int from 0 to 30 of f of t dt. And they said to the nearest whole number, so we'll just round it off. That'll be 2,474, and that's going to be in cars. For part B, they want to know if the traffic flow is increasing or decreasing at time 7 with a reason. So to see increasing or decreasing, we just need to look at what the derivative of f is doing at time 7. So we just need to find f prime of 7 and figure out if that's positive or negative. So going back to Desmos, we can get rid of this integral here. Let's now do f prime of 7, and that comes out to about negative 1.873. And that's cars per minute squared, those units. Now the key here is that this is a negative number. Since that's less than 0, that tells us that the traffic flow is decreasing at 7 minutes. For part C, they want the average value of the traffic flow over the interval from 10 to 15 with units of measure. So for units of measure, let's just figure that out right away. It's going to keep the units of whatever you're averaging. If we're averaging the traffic flow, and the traffic flow is this f of t function, they said that's measured in cars per minute, so whatever our answer is, we're going to write cars per minute after it. Now let's find our answer. So we're going to use our average value formula, 1 over b minus a, so in this case 1 over 15 minus 10, and then we multiply that by the integral from 10 to 15 of whatever we're averaging. In this case, that's the f of t function. And then we're just going to plug this in the calculator. So let me do 1 divided by, that's just 5 there, and then integral from 10 to 15 of f of t dt, which I've already defined f of t up here, and that comes out to 81.899. And again, that's going to be in cars per minute, the units of the original. For part D, they want the average rate of change of the traffic flow over the interval from 10 to 15 with units of measure. So using our AROC formula just on the f function here, we have f of 15 minus f of 10 over 10 minus 15 minus 10. And then let's just plug that into Desmos. So let me make a fraction, and we'll do f of 15 minus f of 10 upstairs, and downstairs we've got 15 minus 10, and that comes out to 1.517. Actually 518 if we round it up. Now for the units, up here we have units of cars per minute. Down here 15 and 10 are minutes. So doing that division, we're going to get cars per minute squared. So 1.518 cars per minute squared. For this calculator-based free response problem, we're told that the rate at which people enter an auditorium for a rock concert is modeled by this big R of t function. It's just a cubic function here, but that's only valid between 0 and 2 hours, and that's measured in people per hour. No one is in the auditorium at time 0, so that's important when the doors open, and the doors close and the concert begins at time 2.
Okay. So we want to know for part A, how many people are in the auditorium when the concert begins. So that's going to be the number of people that have accumulated in there after 2 hours. So to do this, first off, let me just put my R function in the calculator. That would be a good first step on this, regardless of what else I do for the rest of this problem, because I'm going to need it. So we have R of t, and that's 1380 t squared minus 675 t to the third. And again, only valid between 0 and 2 hours. Now, if we want to know how many people are there when the concert begins, we just need to take the integral of this rate of change in the number of people over the course of the 2 hours, so from 0 to 2. So we're going to do integral 0 to 2 of r of t dt. That's all I actually have to write before my answer, because they've already defined r for me. And now let's just go to the calculator and do that. So int for integral, and then 0 to 2, and then big R of t dt comes out to exactly 980 people. For part B on this one, they want to know the time when the rate at which people are entering the auditorium is a maximum with justification. So they basically want us to find the maximum value of R of t. So to do that, we're going to need to find the derivative of R of t, and we're just going to use our power rule on this. So we've got 2 times 1380, and I'm just going to use the calculator to make sure I don't mess this up. So let me just get rid of that. We'll do 2 times 1380, that's 2760, so that's 2760 t. And then we also need to do 3 times 675. 3 times 675 gives us 2025, and that'll be t squared that we're subtracting. All right, so that's my r prime, and I'm going to set this equal to 0 now and look for some critical values. So going back in here, I need a new function for this, and let me just move this so I can see it a little bit better. Okay. So I'm just going to call this little r so I don't mix it up with the other one. I can't call it r prime yet. So let me do little rt equals 2760t minus 2025 t squared. And let me unselect this first one, and let's graph this out now. Now this was on the interval from 0 to 2. So let me do like negative 0.5 to positive 2.5 to focus in. And it's kind of hard to tell what's going on if I'm going like up or down. I see the critical values, but I kind of want to know what my function looks like. So let me make my y values a little bit bigger. Let's go a little more in positive territory. I'll make this 80, 800. Let's make it 8,000. All right, I can see a little bit better now. And let's just come back down. So I see here that we are crossing at about 1.36296. I am going to actually, let me get that number back. Let me copy that. And I am going to let a, just write a constant here, a equal that. So now I can use this number whenever I want. All right, so here's what I did. I graphed it out. I found that I was equaling 0 at 1.36 and some change. So that's my A, that's my critical value, that's in hours. This is the only critical value on the interval from 0 to 2. Now I'm also, to see the maximum, going to test out the endpoints of 0 and 2 as well. So I'm going to plug 0, A, and 2 into the r function and just pick whichever one gives me the highest value. So let me do r of 0 first. So going back here, if we do big R of 0, that comes out to 0, which doesn't surprise us because this was when the doors first opened for people to come into the concert. Now if we do R of A, just replace 0 with A, that comes out to about 854.527. So that's the winner right now. Let's try R of 2. R of 2 comes out to 120. So we can see, comparing these, that the maximum value happens at time A hours. For part C on this one, there's a little bit of reading on this one. The total wait time for all the people in the auditorium is found by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. The function W, which they're not telling us, models the total wait time for all the people entering the auditorium before time t. The derivative of W, they are giving us that. It's this W prime, which is 2 minus t times r of t. Based on all that, they want us to find W of 2 minus W of 1, which would be the total wait time for those entering the auditorium after 1 hour. Okay, so how do we actually figure out W of 2 minus W of 1? Well, we know what W prime is. So it turns out if I wanted to figure out the integral of W prime from 1 to 2, W of 2 minus W of 1 is exactly what I would do in that situation. So let me write that out for you. W of 2 minus W of 1 is equivalent to this integral from 1 to 2 of W prime. And if you're not sure about that, I mean, consider what you would do if I gave you this integral, right? We would take the antiderivative of W prime, which is W. We would plug 2 and 1 into that and then just subtract them. So these are equivalent. Now the reason I'm going with this integral is because we do know what W prime is, and I can easily take this integral on the calculator once I plug everything in. So I'm going to do that now. Let me go back and let me move things so that I can actually see everything. And I don't need this A anymore. This R of t I don't need. Let me define W now. I'm going to call it big W. I mean, I can't call it W prime because it'll get upset if I put a prime in here without first defining the original. So we'll just say big W of t equals 2 minus t times R of t. And let's take the integral now from 1 to 2 of, I'll call it, again, I'm calling this big W of t dt. And that comes out to 387.5. So this would be in hours. For part D of this problem, they want to know on average how long does a person wait in the auditorium for the concert to begin. So the key on this one, we basically have to take the total wait time for everybody from hours 0 to 2 and divide it by the total number of people. That'll give us the wait time per person. Now, how many people were there? Well, we found back in Part A that 980 people entered the auditorium in the time from 0 to 2 hours. So we're going to have to do whatever total wait time we have and divide that by 980, or do 1 over 980 times that number. Now, to get the total wait time from 0 to 2 hours, we're just going to do the integral from 0 to 2 of W prime of t dt. And we're using W prime because on Part C, you might remember when we wanted the total wait time from 1 to 2 hours, we just did the integral from 1 to 2 of W prime like they told us to. So we're just kind of following along with that same pattern here. All right, so let's do this on the calculator. So I've already got, I don't need this, this integral here. I'm going to change this integral a bit. I've already got my W prime entered as W here. So I'm going to do, out in front, I'm going to do 1 divided by 980. And I'm going to change this integral from 1 to 2 to 0 to 2. And what I end up getting for a final answer then is about 0.776. And this is going to be hours. This is the number of hours individually that each person's going to have to wait on average.